Hello, 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 hello. All right, I am coming online now to explain some questions that came forward regarding the slides, the statistics slides, the standard deviation slides. So I want to just specifically answer those questions. So there was a question regarding question 7, and that question asked, slide 7. The question asks, is there a significance other than needing us to see the polarity, the pass fail, that can be represented on a chart? And so what that slide 7 is showing you, what a distribution looks like when it's polarized, where you have grades, where you have most of the students who got A's and then F's. So you can say that that's pass fail. Rarely will we see a distribution like this in a normal math class. And so it could represent pass fail, but it's really just to show you what a distribution would look like. Because what this is getting towards is the normal shape, the shape of a normal distribution, and that's a bell-shaped curve. The shape of a normal distribution. So it's showing you if half of the class got A's and another half got F's, then that's what a distribution would look like. That's really all that it's saying. Nothing really deeper than that. And then we were asked about, I think slides 12 and 13 were the next ones. Let me double check. What is an example of sample mean? Like samples of what? Does it mean samples of school data? So I'm going to go to 12 and 13. Okay. So, a sample mean. So we're getting to the mean is directly the middle of the distribution. A sample mean is it just simply means that you have a sample instead of having the whole population. So say for instance, if you had a math class, and if you took the arithmetic average, which is the mean, of all of the scores of a class, then that would be a population mean. But if you only took, say, 10 of the students and took a small snippet of those scores, that's a sample mean. It's a sample of your population. And in research and in counseling and things like that, rarely will we get a population mean, because rarely can we get access to everybody who we are attempting to sample. So we usually go after what's called a representative sample of the population. So we make sure that there's some characteristics that are consistent and that are static, that we can say after we get our outcome, that we can say with confidence that this outcome that represents the sample can be inferred to the population who they are representing. So that's all it is. It's a small sample of the larger population. So we've got an average. We have a mean of a sample of the population. It's nothing more deeper than that. And let's see. I think that was 12 and 13. Let's look and see. All right, slide 13. Why are the mean, median, and mode the same values? They're not the same in math class, so why now? Is it because of the use of the curve, like because they'd always be in place in the middle of the standard deviation? So you almost got that right. You almost have it right. They may not be the same in a math class because when we're dealing with math classes, the distributions are not always normal. When we're dealing with a normal distribution, which typically we find a normal distribution throughout nature. And typically when we look at almost anything, shoe sizes, women's shoe sizes, men's shoe sizes, average weights in America, in whatever country, hair color, colors of kinds of fruit, whatever it is, there's a natural phenomenon in nature that most things normalize to where they can be represented on a graph. And if we were to chart them, it would be this normal up, 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 and then down distribution. And so to answer the question, when we have a normal distribution, you have the mean, the median, and the mode right smack dab in the middle. The mean, which is the average of the population, is the average of your sample. It's always going to be right in the middle. And then you have the median. The median represents 50% of your data falls to one half, and 50% of your data falls to the other half. So your median will always be right in the middle in a set of normal data that's normally distributed. And your mode is that indicator, that item, that sample that occurs the most often. So if you had, a score, all these scores, and if you've got a peak, then there's a score that's going to keep repeating in order to make your peak. So your mode is that item that occurs the most. I can't think of the word, but at any rate, that piece of data that occurs the most often, or the score, the integer that occurs the most often. Okay, so that's why they align, but they'll only align if the data is normally distributed. All right. And then you ask about slide 14. The shape of the curve is determined by the standard deviation and the mean. How is this possible if the example later is in the presentation with the SD minus 15 and SD 5 looks the same in the picture? When I look at the slide number 16, the curve with less variance looks much different. Is this what you mean? Because there is a standard deviation that seems much smaller. I should have looked at that closer before I started. The thing is this, if I've got to talk about that a little bit more, I will. The thing is this. How is it possible? The standard deviation and the mean. The smaller the standard deviation, the more narrow the curve is. The wider the standard deviation, the more distributed the curve. And so the standard deviation represents the variation that's in your data set. So if you have a lot of scores that fall really close to the mean, you're going to have a tall peak. If you've got a lot of scores, right, where people fall on the line, on the x-axis where they fall, then you're going to have a lot of spread. So if you got a mean of 50, and you've got scores that pretty much represent between 70 and 90, then you're going to have a high peak. But if you got scores that go all the way down to 30 and 100, you're going to have a more spread out peak. So that's really how it's determined. So the smaller the standard deviation, you have lower variance. The higher the standard deviation, you have more variance. That's the best way to explain that. And I just took here number 16 with that discussion. So 16, do you mean because the higher amount of hours is more concentrated instead of spread out? Absolutely. That's what I mean by 16. And then 29. Why is it 50%? I know it says 50% of variables are higher than the median, but how do we know that? Is it just a standard statistic? So let me see what I ask on 20 in order to answer that one. What slide 20 says. Percentage. What did you ask? Let me see. Go back here. Oh, slide 29. Slide 29. All right, let's go to slide 29. Okay, yeah, it's just the rule, because it asks what percentage of the light bulbs are expected to last 1,000 hours or more. 1,000 hours or more. And if you look at that slide, the mean, the median is, so basically right here is better to talk about the median, because the median, there's always 50%, and this is a statistical rule, a mathematical rule, really. There's 50% of the data that's on this side to the higher than the mean, and 50% on the data lower than the mean. And if you look at that slide 29, and you go to where 1,000 is, it's right there in the middle. So there's 50% of the data, 50%. So to the right, it represents 50%, right? That the light bulbs, what percentage of light bulbs are expected to last? 50% of the light bulbs are expected to last at 1,000 hours or more, because 50% are to the right of the mean. It's as simple as that. All right, just a couple of more questions and we'll be done here. We're at about 10 minutes, okay? Let's go back to our slide 30. Am I correct that we need to subtract the original score from the mean score to figure out our deviation? Is Rhodey's score further down the curve because of the lower deviation number? Also, where did we get 5? Is that just the sake of the sample? Yeah, that's the data that was given us. So we some data, we needed, they gave us that data in order to know, they gave us that data in order to know, how to, let me get to it. Yeah, they just provided us the standard deviation. Because you would have had to compute. You would have had to compute the standard deviation, and that's, I'll do a slide on that. You would have had to compute it from the raw data. You can only get that from the raw data, and so basically the standard deviation computation, it's the sum, it's the square root of the sum of the squared deviations divided by n minus 1. It's the square root of the sum of the squared deviations divided by n minus 1. And so I'll do a video just on how to calculate the standard deviation. So in this sense, they gave us the standard deviation. They gave it to us. So that's where we got the number from. And then your question, your other part of the question was, in order, am I correct, we need to subtract the original score from the mean to figure out the standard deviation? No, that's not correct. There's a totally different, that's how you figure out the standard score, not the standard deviation. How you figure out, 1 second here. So we, the standard score, not the standard deviation, right? The standard score, or the raw, the z-score. That's how you figure out the z-score or the standard score, right? All right, so we're wrapping it up here. Let me go back to the question. So you figure out the z-score, which is z or standard score, which is your obtained score. It's right here on the slide. So it's right here on your slide. It is on, your standard score, your original score minus the mean divided by the standard deviation is how we get our standard score. So our original score minus the mean divided by the standard deviation, that gives us our standard score. And that's what these particular slides are doing here. And then I think we're at our last question. When I worked Sarah's math, I got the correct z-score. But when I worked Michael's math, I didn't get a decimal. I got a whole number because a half of 4 is 2 in regular math. Should I just always make any true halves a 0.5 in this situation? Okay, now I didn't look at, let me see. Because, so we're dealing with, All right, so if we remember our equation, so we had Micah's score. So hers was, so they both had 2 as their, wait, I'm missing something here. What am I missing? All right, as their outcome. Because for both of them, we had, both of them had the same original score of 92. Is that correct? Yeah. Both of them had a raw score of 92, and both of them had a mean of 90. So they both ended up with the same standard score. But remember, in order to calculate, they ended up with, well, you haven't finished calculating it. That's the piece. So you got to take the original score minus the mean, right? And so they both had the same original scores, and they both had the same mean, but they had a different standard deviation. And this is what gives you your difference. Because now, in order to get the standard score or the z-score, we take the original score minus the mean, and we divide it by the standard deviation. And so both of them had they both ended up with 2, but they had different means. And so Micah's mean was a 4, and Sarah's mean was a 2. And so if you divide, so you take that outcome, that score, and you divide it by the standard deviation. If you divide 2 divided by 4 is a 0.5. 2 divided by 4 is a 0.5. 2 divided by 2 is a 1. So that's why you get a one half step from the mean. So if their mean in here was, their mean was 90, and so Micah went only 1/2 step up, and Sarah went a full step up. So that meant if we're going to the right of the mean, that means our numbers are getting higher. The numbers are getting stronger. So whoever goes furthest out to the right, their raw score is the stronger score, So in this case, Sarah ended up with a stronger 92 than Micah did because theirs was more spread out. And so if you've got to take more steps to get somewhere, then that means that you're further out. If you've got to take less steps, so she took a 1/2 step, so it didn't take her further out in the distribution, closer to plus or minus 3 or plus 3, if you get what I'm saying. Okay, so basically, because her standard deviation was smaller, right, then she moved only a 1/2 step. And her standard deviation was more variation. It was larger. So she only moved a 1/2 step. And the other standard deviation was smaller, so she moved a larger step. Because the more spread that you have, the wider it is. So if you go back, let's go back to, if you go back to slide, what slide is that? Slide 34 and 35. On slide 34, it shows us that Rhodey's standard deviation was 15, and her score was 235. So for Rhodey, she had to move one step. She only had to move one step to get to the 235, right? Because her standard deviation, so she had a lot of movement in her standard deviation. It was a lot of spread in her standard deviation. So it only required her to have a small amount of movement. So one step Standard deviation was 15. And so that means one standard deviation below the mean. She was one standard deviation below the mean because there was a lot of spread. Because the standard deviation is 15, each increment is 15. Each way is 15. So she only had to move one time to get to her score of 235 because she had a larger standard deviation. But when her standard deviation was 5, still had the same raw score of 235. So now she's got to move 3 times, right? And each time you move, you're moving away from the mean. And depending on what it is that the distribution is representing, it may be beneficial to move one standard deviation or 2 or 3 above the mean. But here we're talking about math scores, I believe. Or no, what are we talking about here? Say, for instance, if we were talking about math scores. If we were talking about math scores and she is 3 steps below the average, then that's a problem. But if we're talking about math scores and she's moving 3 steps above the average, then that's fine. Do you see? So if we were talking about math scores here and she is moving and her standard deviation is 5 and she's got a 235, right? It's not a good example actually, but she's moving 3 steps down. But if her standard deviation was 15 and she's only moving 1 step down, she's still kind of close to the average. She's still close to the average. So at any rate, ask me more questions and I will provide you with as much information as I can. Let me just say this to round it up. The smaller a standard deviation is, that means you have less spread and you're going to be closer to the average. So what situations do we have that it's better to be closer to the average than more of an outliner to the left or to the right? The larger the standard deviation, your curve is going to be smaller, and instead of a peak where you're going to have a spread of numbers more so, then the numbers all kind of centering around the average. There are times when it's better to have a spread of number, but that just represents dispersion and not so much a peak, right? Not so much a peak. All right, I'll talk some more specifically about each one of these concepts. So right now, this just answers the questions. All right, talk to you soon. Bye-bye.